All right, let's now take a look at the reminders. Your written test number 2 from yesterday, I'm going to release the result by early Monday. So when you check your E-class announcement first thing in the morning on Monday, you will see the result. Okay? And then your lab number 4, don't forget it's due tomorrow noon, not midnight. And make sure you submit your best attempt in time to claim your credits. Although I already released the grading test and solution video for your lab number 4, the intention is for you to choose the better way for you to get prepared for programming test number 3 on the coming Wednesday. You can either choose to work on your own for lab number 4 until the submission deadline as much as possible and then look at the solution after. That's okay. Or if you want to take a look at the solution right away and follow me along with the solution, that's also fine. Not a problem. Choose the one that works better for you. So the solution and the grading test for your lab number 4 are already there. And your programming test number 3 that'll be the final test before the exam. So that will be next Wednesday during your enroll session. Okay, just make sure you show up to the right session. There will be one more bonus opportunity for you guys. So it's basically the formal course evaluation online. I believe that's going to be launched November 18th, which will be Monday. I'll send you guys another reminder. So the same rule as last time. If the collective response rate reaches some threshold, then I'll be happy to give everybody some bonus mark at the end. Right? Of course, it's completely anonymous. I will not be able to see any of your feedback until I release the final grade next year. So you can feel free to say anything you like in the course evaluation. All right, guys, any questions about the course? Yes, absolutely. Go ahead. Okay, sure. I can definitely try to do that, but we may need to wait a little bit. But for now, as long as you have submitted your lab in time, you can definitely assume you got full marks. Yeah. Okay. All right. And I will also reach out to you guys about the review session for the exam. We can talk more about it maybe next week. But I know our exam is pretty early. You only got maybe only a few days after the study day before the exam. But, I will see how much I can help. All right, let's now do a recap about Tuesday's lecture, and then we'll continue from there. So for Tuesday, we basically talk about number 1, the intuition of dynamic binding, and we're gonna revisit the same idea today with a little bit more definition about what will be the circumstances where a reference variable might change its dynamic type. There are 2 scenarios which we'll cover today. And from Tuesday, make sure you know how to filter a table like this. When you're given a piece of code, after, for example, after here, how would the dynamic type of the variable change? And how is the static type going to remain the same always? Right? Just remember. And we spoke about whenever we talk about compilation, only look at static type. Whenever you want to analyze more behavior about a runtime, you have to look at dynamic types. So today, I'm going to talk about a full story about typecasting. And we're going to revisit this example very, very closely again. Okay? We'll get there towards the second half. And we'll talk about multi-level inheritance hierarchy. So either this one here or this one here. I will highly recommend when you guys study for the exam, try to look at each or at least one of the hierarchies and revisit the 2 designs without inheritance, contrast them with the design with inheritance to see what will be the corresponding actions you will have to take to implement the multi-level inheritance hierarchy using this, or this. All right, that's something I will expect you guys to try it out before the exam. And we use this diagram here to define 2 terms. We talk about given a class, what will be the ancestor? And given the same class, what will be the descendants, right? So ancestor will be the class itself, the class it directly extends, also all the classes it indirectly extends, right? We so-call this ancestor path all the way to the top of the hierarchy. The other direction will be we got the class itself plus classes that directly extends it, and also all the classes that indirectly extends it. We call these the descendants of A. What's really so special about descendants, for example? All the descendants of A can fulfill the expectation of A. That's a very important insight because we know the lower the hierarchy is, the more attributes and methods you can accumulate to the subclasses. So that's why whenever you're expecting, let's say A, what can I substitute A by? I can substitute A by any of its descending classes, including itself and all the classes underneath. On the other hand, I cannot substitute A by its parents, or I cannot substitute it by its grandparents, and etc. That's something very important. We're going to revisit the rule in a moment. And that's the example we did, just to say, given some class, how do you figure out its ancestor, descendants, and expectation, right? That's something I also expect you guys to know. Okay. And we talk about the expectation, right? That's just another view from it. And we talk about substitution. So the way we do variable assignments, when you say V1 is assigned to V2, the new interpretation is we want to substitute V1 by V2. Whether or not this particular substitution should be allowed depends on the relationship between the static type for V1 and the static type for V2. And that's something I will make it very precise in just one moment. I need to revisit some rules together with you in just one moment. And yep, variable assignment, that's something I'll review. And then expectation, as we said. So basically, the lower the class is in the hierarchy, the more expectation you can have. For example, if you look at these two variables, you get Jim and Alan. Jim has the static type over here. Alan has a static type over here. Because Alan's static type here is lower in the hierarchy, so you can expect more attributes or methods that can be called on Alan. All right? All right, that will be it from Tuesday. Any questions? Let's now try to be very precise about what I meant by substitution rules. And I'm going to generalize it very carefully together with you. Okay, we're going to revisit this diagram here, but I'll show you where you can find the corresponding point in the slides. It will be slide 44. Okay, so in slide 44, when you read it along, but it's kind of abstract, so that's why I need to visualize together with you. So there are 3 rules that we have to follow. Okay, rule number 1 about safety, rule number 2 about what's unsafe, rule number 3 about what's unsafe as well. All right, let's take a look one by one. So the starting point is this. Let's say you have a reference variable of static type A. This is what I start with. Okay. Let's say I have OA, reference variable, declared to have static type A. All right, that's something we start with. And then I'll tell you the question you want to ask yourself in order to understand the rule. So think about the A over here is the static type of OA. And I'm just going to mark it in the diagram here. Right? You can see it sits somewhere in the middle of the hierarchy. And then let's say we got another reference variable OB, and I put a question mark here for its static type, meaning that's open at the moment. And then we try to say OA is assigned to OB, or we can say OA is meant to be substituted by OB. Here's the following question you want to ask yourself implicitly. Okay, I'm going to write it down. In order for this substitution to compile, what can be the range of static types of OB? Notice that I say range. That means there could be more than one. That's valid. All right? So I'm really talking about if I try to somehow assign OB into OA, what are the allowable static type for OB? Here is the principle. Any class that can fulfill the expectation of the static type of OA will do. That's the principle. Otherwise, it's not allowable. Any class that can fulfill the expectation of OA, which is left-hand side. OA's static type will do. Right? That's the most important intuitive statement you want to remember. Okay? And when I say any class that can fulfill the expectation of static type of A, that means any descendant class of it. Because we know this descendant class of a class can always satisfy its expectation. All right, let's now go over the rule before I write, after I write this down. That means any descendant class. Okay, yeah, let me write it more properly. Start. That is any descendant class of A. Because we know that at the moment, OA has a static type A. Any descendant class of A can fulfill its expectation. All right? Descendants, that's the key word over here. All right, let's now go over the rule one by one. And then we'll do examples. Rule number one. And that's the only scenario where the substitution is going to be valid. That's the only one. It would be safe to substitute A by any type that's a descendant class of A, like what I said. Right? Any descendant class. All right, that's case number one. I can substitute OA over here by any type of OB, that is A itself, that's okay. A can satisfy itself. Or any of its descendants over here. Okay? So the way to draw that would be like this. Think about here, this range over here. All right, descendants. Okay? So this set of classes will be descendants. Descendants of A that can serve, that can fulfill. Fulfill the expectation of A. So they can serve as the static types of OB. All right? They can serve as a static type of OB. Right? You can see OB is over here. In order for OB to have the valid static type, to make the equality, to make the assignment work, it must be able to fulfill the expectation of the static type of OA. All right? So that's the logic. Any questions so far? That's rule number one. And that's the only scenario where it's going to be safe. And there are two cases where we don't have the safe substitution. Basically, if you give the static type of OB something here that cannot satisfy the expectation of OA static type, which is A, what would that be? For example, if I give the question mark over here to be this class over here, that's the parents of that. Parents always assume to have less expectation. So the parents is not good. Grandparents also not good. All the way to the top. Basically, any of the ancestor of A's parents over here cannot be good. That's case number two. All right? So if you look at rule number two on the slides, it would be unsafe to substitute A by a static type that's the ancestor class of A's parents. Be careful here. I didn't say A's ancestor because A's ancestor includes itself. Okay? You cannot substitute it by A's parents' ancestor. So what we have, the case number two. So this will be A's parents and all the way up to the top. All right? So here would be the ancestor of A's parents. They cannot fulfill the expectation of A. they cannot fulfill the expectation of A, so they cannot serve as the static type of OB, which is here. All right, that's rule number 2. Rule number 3 is very similar. The classes that we haven't really covered in the hierarchy are classes like this. For example, there is one class over here. If you remember how we call them, sibling. Remember? So this class and A share the same parents. For example, resident students and non-resident students. In general, we say that any class that's neither ancestor nor descendants has incompatible expectation as a class. So now resident students and non-resident student, they got incompatible expectation because you got premium rate in one class, you got discount rate in the other class. Incompatible. They're simply different. So that'll be rule number 3. So rule number 3 tells you it will also be unsafe to substitute A by any class that's neither ancestor nor descendants of A, because they got incompatible expectation. All right, so that'll be the last case. So one here. Let me draw a little bit better. One here. All right. So these classes, as you can see, they are not really along the ancestor or the descendants branch. So they are neither. And they got incompatible expectation. So one here, and also one here, for example. So these are neither ancestor nor descendants of A. That means they got incompatible expectation. All right, so that's case number 3. So there's only one case where you can substitute A by its descendant classes on the right-hand side. In the other 2 cases, either ancestor for the parents or neither ancestor nor descendants, you cannot substitute it. So there are 2 cases that's unsafe. All right, that's the most general way to say the substitution rule. And we're going to use this general principle here to do some example, just to emphasize. Any question? All right, let's now do some example. Let's say here we got 2 variable assignment here. I'm going to do one of them, and then the other one will be left to you. Let's say this one here. All right. Should this be valid? All right. The way to see will be like this. SP1, the left-hand side, has the declared type iOS. You can mark it down right away in the hierarchy, which is over here. All right. And then SP2, since we only talk about compilation, you only need to look at static types. SP2 was declared to be iPhone SE, which is here. So the variable assignment here boils down into, can you substitute this class by its descending class? Yes. So that compiles. All right. All right, that's exercise number 1. And you can do the other one as exercise yourself. Compile. Because SP2's static type, which is iPhone SE, is a descendant of SP1's static type, which is iOS. So this is the kind of complete answer I would be expecting you guys to write. Okay, compiles, that's part 1, and this will be the explanation. Okay, and of course the descendants can fulfill the expectation of its ancestor. All right, question here about the example here. So this example here basically belongs to substitute A by one of its descendants. So we talk about the green area. Let's now take a look at what about this one here? And what about this one here as well? Right? Let's see some example here. Let's say we got SP1 is assigned to SP2. How do we do that? Again, similar annotation. SP1 has the static type iOS, which is over here. And we got SP2, the right-hand side, has the static type smartphone, which is over here. So the question boils down into, can we substitute iOS by smartphone? No, because smartphone is not a descendant class of iOS. All right. So this is some detailed explanation you have to write in the exam. How would you write it? You would say something like, no, does not compile. I'll first of all say it does not compile. All right. The reason is as follows. The static type of SP2, which is smartphone, is not a descendant class of the static type of SP1, which is iOS. Question? No, sorry, let me stop you, sorry. You can assign iOS to smartphone, but not the other way around. So over here, we are assigning SP2, which is a smartphone. We are assigning smartphone into iOS. That's what's not allowed. I want to make sure. Yes, that's correct. That's correct. Good question. Good question. The answer, so very good question. So your class may ask a very important question here. Hypothetically, let's say we don't have the FaceTime. Okay? In that way, at the moment, at this very moment, iOS and smartphone have the same set of attributes and methods. Now, can I say I want to assign smartphone into iOS given that they seem to have the same expectation? The answer is no. The rule is simple. You can only do the assignment if this is a descendant class of that. The reason that you cannot allow that to happen, even though at the moment they got the same expectation, is because in the ongoing basis or in the long term, it will be very, very rare if you don't add any new attributes or method to the subclasses. At some point you will, just not now. That's why you wouldn't allow it now. All right? No, you will not compile. Because you think about this. Let's say at the moment they have the same expectation, you allow that to compile. 6 months later, you add some new attribute to it, suddenly stop to compile. Nobody likes this inconsistency for the compiler. Okay, that's why. It's a very important question here. You want to make sure you always understand compiler doesn't care at the moment what attributes and methods are really stored in your classes. They don't check. They only check to see whether this is they only check to see whether this class extends indirectly or directly iOS. If it does not, doesn't compile. As simple as that. Okay? All right, this one here. This will be another case of unsafe substitution. This one here, let's do the same principle here. SP1 over here has iOS as a static type, which is over here. And then we have SP2, which has the static type Huawei i50 Pro, which is over here. Now, the question boils down into, can the static type of SP2, which is this guy here, Huawei, can it fulfill the expectation of the SP1 static type, which is iOS? No, it cannot. It will only fulfill if it will only fulfill if this class was its descendants. No, it's not. Okay, it's neither ancestor nor descendant, so it's not going to work. Okay, so this one here, no. And this one corresponds to this case over here, right? Neither ancestor nor descendants. But you can simply say, again, similar. You can say the static type of SP2, which is Huawei IP50 Pro, is neither an ancestor nor, forgive my writing, nor descendants of, okay, I'm going to continue to here, nor of the static type of SP1, which is iOS. Right? The principle is very simple, and you apply that to every example. All right. Neither an ancestor nor descendants. All right, that's a critical term here. All right, question. If no, let's now move on. All right, so we're going to talk about dynamic type. We'll revisit this substitution rule very soon. We're going to need that very badly for today. All right, so we talk about how we can visualize static type versus dynamic type. That's kind of important, especially when we talk about typecasting in a few moments. Okay, dynamic type. Definition, dynamic type is simply the type of objects that you're currently pointing to by the variable. Because you can point to any object at any time, so that means your dynamic type may change over time, not static type. And there are two possible ways for you to change the dynamic type. That's something I'm going to show to you. Two possible ways. Before that, let's talk about how you can visualize. Well, you already know how to visualize diagram, right? Visualize objects. But how do we distinguish between static type and dynamic type? If you look at the slide, they tell you some principle, but let's see some example here. If you look at here, we got S declared to be of static type students, right? You can annotate right away. The student over here is the static type. And then we try to initialize the S to point to a new resident student objects. All right. So this is approach number one. How do you modify the dynamic type of a reference variable? If you simply just let it store the address of some new objects. So why is this valid? Simple. All you got to ask yourself is, can resident students dynamically fulfill the expectation for students? Indeed, it can. It's a descendant class, right? Simple. So this will be the dynamic type. So this is why this will compile and this will run at the runtime. This will be dynamic type. And how do you visualize that? You pretty much know already S pointing to some resident students object. That's nothing new. But I would say sometimes you might find the need to also put besides the reference variable its static type here. It can also help clarify the issue, especially if you try to say, for example, S dot premium rates. This should not be allowed because PR is not part of the expectation for students, right? So this one here in the diagram is the static type. And this one here in the diagram here is dynamic type. Right, so the only thing new is about including the static type in the context of your diagram. It might help sometimes. Okay. If no question, let's now talk about how you can change dynamic type. The approach number one, you basically just keep reassigning the reference variable to different new objects over here. Right, that's basically what you do. And that's something we actually did earlier on Tuesday. Okay, let's now revisit this example again. Number one, you want to know whether or not this assignment here should compile. This will compile because the new dynamic type over here, which is resident students, can fulfill the expectation of its static type, which is students. Right? That's very important. And the reason that it can fulfill is because resident students is a descendant class of students. That's the reason, right? To be complete, you should also say resident students is a descendants of students. And similarly, you can also argue that this assignment here is also valid because non-resident student here is a descendant class of students, right? The same. But let's now talk more about dynamic type. Given that these two variable assignment will compile, what's going to happen at the runtime? That's something we trace on Tuesday, right? I may not repeat, but let me remind you the details. After the first reassignment, at this point here, the dynamic type of Jin has become resident students, right? And after the second variable assignment here, after that, at this point over here, the dynamic type of Jin has become non-resident students, right? You can also feel free to redraw the object structure and see which object it is pointing to. That's how you figure out dynamic type. So that's approach one about changing the dynamic type, which is pretty straightforward. Two things you want to really make sure you review. Number one, how do you judge to see whether the assignment itself will compile? You got to make sure the new class name over here should be a descendant class of the static type here. That's number one. Number two, at the runtime, after executing this, you will only change the dynamic type for the reference variable to this class over here. It doesn't modify the static type. All right? Question? All right. If no, move on. What about this one here? What will be the dynamic type for Jeremy after executing this assignment? Oh, what do you mean? You nod your head. Doesn't compile. Good man. All right, doesn't compile. The reason that this doesn't compile is, if you look at this class here, students, is it a descendant class of resident students? No, it cannot fulfill its expectation. Does not even compile. Very good. Because students is not a descendant of the static type of Jeremy, which is resident students. All right. Good. Compilation first before even talk about what's going to be dynamic type. All right, so this one here could be also something you can trace, but let me trace on the diagram just to show to you. So what we have is we got my phone declared to be Android, which is over here. That's a static type. Think about what would be the allowable compilable dynamic types I can assign to it. Any class that's going to satisfy the expectation of Android should do, which will be Android itself, its descendants over here. So any one of these should be okay. Huawei i50 Pro is one of them. Galaxy S21 is one of them. So both of them will compile. All right. And then, more importantly, after this one here, dynamic type will change to here. After this one here, dynamic type will change to this one here, depending on where you actually asked about the dynamic type. We'll learn about an operator to check the dynamic type on Tuesday, not today, but we'll learn about it. Now, just on the paper, you should know when the dynamic type will change. All right, for what it's worth, let's now put it here. So at this point here, after the first reassignments, dynamic type changed to Huawei P50 Pro. And then after the second reassignments, dynamic type changed to Galaxy S21. Right, similar, right? All right, this one, how about this one here? iOS, static type. Now, I'm trying to give a dynamic type, Huawei i50 Pro. Can it work? No. Very good, right? You can see the only classes that will work will be iOS, iPhone SE, or iPhone 13 Pro. Agree? These are the only three classes that can satisfy its expectation. This one here, no, not good. This one here is here, also not good. All right? Both of them, not good. And the reason will be, like what I wrote earlier. You would say, for example, this class over here is not a descendant of the static type of my phone, which is iOS. Okay, hopefully as we do more and more exercises and try to revisit this idea, it's not too bad. Yes, question.
It's very likely that the answer is no, but just to confirm, can a class have more than one part? Like, can it extend more than one class?
No, you cannot. So can a class extend more than one classes? No, you cannot. So luckily, that would make things simpler for us, right? So whenever, let's say you start from the class, if you want to figure out all the ancestor, you follow just a unique path all the way to the top. So you only got parents, and then parents, parents, and etc. You don't have to branch out. You don't really have to. Okay. Okay. And by the way, in 2101, the next turn, you will be asked to implement programmatically to say, for example, given a class over here, return an array of classes that are its ancestor. That'll be interesting to program. Anyway, not now. Question.
You have the dynamic type of this child class and this parent. Can that dynamic type have any access to any of the attributes of the descendants?
Josh, can you say that again? I don't quite catch you. Say that again.
Okay, so if you have an android, you're setting it, you're changing its dynamic type to a Huawei P50 Pro.
So you're saying this is dynamic type for now.
Well, that's the static type, but then you change the
Okay,
dynamic
let's say,
type.
okay, you're saying this is static type now.
Yeah,
And what about dynamic type?
and if dynamic type is set to Huawei 50 Pro,
Let's say, okay.
any of the characteristics of that Huawei 50 Pro, usually it's not inherited by the parent. Does the parent have access to any of those unique attributes?
Okay, let me try to answer briefly here. So if I'm here, Huawei P50 Pro, it basically inherits all the attributes and methods along the ancestor path, everything. Not just the parents, but parents, 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 all the way to the top of the hierarchy. That's something to note.
But when you change the dynamic type, what is really the purpose or the usefulness of doing that to a Huawei 50 Pro?
Okay, it could be, for example, let's say I got a smartphone here. If I got dynamic type iOS, for example, in that way, when I say my smartphone surf web, because the dynamic type right now is iOS, it's going to, according to dynamic binding, call the surf web using Safari. And then let's say I'm not happy with Safari. And then I can say, no. Now reassign the dynamic type of smartphone into Android. Now if I call smartphone the surf web once more, it's going to, according to dynamic binding, call the surf web with Firefox. So dynamic type somehow allow you to choose different version of the method that has been overridden in different descendant classes. And which one that's going to be called depends on what's the dynamic type at that moment of method call. That's something we'll see more example about.
So it lets you get access to the overridden functions within.
Absolutely, you can. Yeah, you definitely can get access to overridden method for sure. Yeah. All right. All right. So this one here, that's also something we did earlier. So all I want to say is, when you see these two method called gym.getTuition over here, right? You can see the same method call getTuition and getTuition. But if you look at the hierarchy over here, we actually got either the getTuition from the student class, guys. Hello, please. We got to get tuition here, and we got to get tuition in the resident students. We got to get tuition in the non-resident student. We got three different versions over here. Okay, so now which version is it going to be called? Because if you call this version here, it's going to use premium rates. If you call this version here, it's going to use discount rate. So for this one here, right, as we said earlier, at this point, Jin is actually going to have the dynamic type of resident students. At this point over here, Jim is going to have the dynamic type non-resident students. Because the dynamic types are different, when you call the same overridden method, it's going to invoke different versions, right? Right? That's something we said earlier, right? I just want to highlight it. Always remember, when you got multiple versions of the same method that's kind of overridden in different descendant classes, which one should you choose? Look at the dynamic type. Okay? All right, one more note. So the get tuition here will be the version from resident students. And this one will be the version from non-resident students. Of course, this version here is going to use premium rates, and this version here is going to use discount rate. All right. How about this one here? Now I want to say rs.get tuition and nrs.get tuition. Now, which version is it going to call? Doesn't compile. I like that answer. Why is that not compiling? The other way, you cannot assign ancestor class to descendant class. I know that's what you meant to say. Okay, good. No problem. I love the answer. This one does not even compile, right? So it's a tricky question. I agree. If I ask you in the exam, what will be the version of get tuition being called? You should tell me that it does not even compile. All right? Because Jin has the static type students, which is here, which cannot fulfill the expectation of RS static type, which is resident students here. All right, does not compile. Good. All right, any question so far? Okay, we're now to a point where we can introduce the two terms, polymorphism versus dynamic binding. They kind of go together. Dynamic binding is more like the consequence of polymorphism. So if you go back to the slides, so these are all the examples we have gone through. All right, you can also take a look at the slides. Might give you some different perspective, but we didn't skip anything. If you look at slide number 49, so that's the definition for polymorphism and dynamic binding. So for your knowledge, poly simply means multiple. Morphism means shape. All right, I guess maybe from Latin or maybe somewhere. I don't know. That's what I read from the books. So polymorphism simply means multiple shapes. Shape means dynamic type. So we are saying that for any given reference variable, if you have some inheritance hierarchy in the context, what can be the possible dynamic types for that particular reference variable? It can be any of the descendant classes of that particular reference variable, static type. That tells you you may have multiple possibility for the dynamic type, so you got multiple shapes at the runtime. All right. That's something you will see on the slides, but let's now take a look here for one example here. Okay, why don't we take a look at this example here? That's something I just mentioned when I responded to Josh's answer, but let's revisit that. This one here is similar. Okay, let's now focus more. This one is a bit slightly newer to you. Let's say we got SP1 and SP2. Okay, and then so SP1 over here. First of all, you can see SP1 has the static type of smartphone. The fact that we declare SP1 of static type smartphone tells us, according to polymorphism, SP1 can have multiple possible. I'm not saying it can have multiple dynamic types. You can only have one dynamic type at a time. I'm saying multiple possible dynamic types. Dynamic types, which will be the descendants of smartphone. How many are they? If you look at the diagram here, smartphone, oh, sorry, too big. Smartphone is here. That's a static type. What would be the possible dynamic types? Well, all the descendants, which can be smartphone itself and all the other classes. Anything is possible because anything underneath is a smartphone. That's polymorphism. Okay, and this particular case over here, let's say SP2 has dynamic type Galaxy S21. After doing SP1 equals SP2, right? If you look at this line over here, this variable assignment here changes SP1's dynamic type from used to be iPhone 13 Pro to start with. iPhone 13 Pro to, since we are trying to let SP1 point to wherever SP2 is pointing to, if you draw the diagram. So SP2 has the dynamic type Galaxy S21. So that will be the new dynamic type, right? 2, Galaxy S21. So we are changing the dynamic type from one to another using these reassignments. Right? So what's really dynamic binding? Polymorphism, again, tells you SP1 here may have either this as the dynamic type or this as the dynamic type because they're both descendants of smartphone. Dynamic binding goes further to say, depending on what's the current dynamic type for the reference variable, you're going to call the corresponding overridden version of the method in that particular dynamic type. For example, at this point over here, SP1, its dynamic type is iPhone 13 Pro. That tells you that the surf web method here is going to call the version from iPhone 13 Pro, which is going to use Safari, right? On the other hand, when you try to call surf web over here, because we know that at that point we have already reassigned SP1 to SP2. So now SP1 over here has a different dynamic type, which is Galaxy S21. And when you call surf web, it's going to call the version that's in Galaxy S21. And that one there, let me zoom in a little bit. That one there inherits the version that's actually from the Android, which is going to use Firefox. All right, so different version, depending on what the dynamic type is. Recap. Polymorphism tells you a reference variable can have any of its descendant classes as the dynamic type. Polymorphism, multiple shapes. Depending on what the shape currently the reference variable is, you're going to call the corresponding version of the method. That one's dynamic binding. All right, you want to revisit these two definitions very closely, okay? And then use the example that we spoke about. Okay, question. All right, if no question here, let's now move on. So the next point will be about casting. Right, so we are done with polymorphism and dynamic binding. Let's now move further to talk about the missing puzzle for typecasting. So we are done with this, and all the examples have been covered. All right, so we can move all the way to. I think that the only this one we also covered. I think that this second part over here is something that you can also refer. You can revisit yourself. Okay, that's a little bit new, but same principle. And this one as well. Surf web, we talk about it. Okay, casting. All right, so starting from slide number 55, we're going to talk about typecasting. Let's take a look. All right, we're still using our familiar classes here: student, resident student, non-resident students. That's got 3 lines of code over here. Let's trace the code. Well, actually, even before that, does what I have written here compile? Does this compile? We're asking whether resident students can fulfill the expectation of students. Yes. All right, so this is good. And can I reassign RS to Jin? All right, if you say no, that's very good. I like it because Jin has a static type students. Can students fulfill resident student? No. So this piece of code at the moment does not compile for the reason we know pretty well. But I would like to visualize what's happened so far, and I want to criticize about the Java compiler being so unsmart about what's going on here. Okay, let's see what's going on here. After line number 1, we basically got Jin declared to have student type, pointing to an object dynamically of type resident students. Let's visualize that. Resident student, of course, presumably it has some premium rate. And then in line number 2, which doesn't compile, let's think about what we intend to do over here. What we intend to do is like this. We say we declare some reference variable RS of static type resident students. I simply just want to let RS point to the same objects that Jim is pointing to, which makes total sense because RS being declared as resident students will only be expected to use as a resident students, which is okay because I do have premium rate here dynamically. Somehow the compiler is being so stubborn. The compiler say, no, 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 you cannot do that. Because if you say, if you want to assign RS to Jim, that means this RS must be a descending, that means the student here must be a descending class of RS. Since it's not the case, you cannot do it. Since like the compiler is not really keeping track of where Jim is really pointing to dynamically. Otherwise, it would have just allowed RS to point to resident student because I'm using it as resident students. You see the logic here? So the compiler seems to be very, very unsmart. Not very smart, how about that? And because of this, I would like to give you guys some, I call A+ challenge. I'm going to describe a problem to you. If you can develop a solution in any programming language, in Java, C, Python, C++, anything, if you can write a program as I described right now, I'm going to give you an A+ right away. You don't even need to write the exam. Even if you fail the exam, that's okay. I'll still give you A+ if you have that program written. Here's the problem. Okay, listen carefully. Your program here, again, you can write in any programming language you like. It's going to take two inputs. Input number 2 is going to be some name of variable. For example, S. The first input is going to be some Java file, only a single file. Okay, like a main method. Let's make it even simpler. Okay, it could be, for example, the myClass.java has some main method here. It declares S to be students, and then it does something in the middle, whatever you like, and then at the end, it says S is reassigned to resident students objects. This tells you the last dynamic type for the S should be resident student. Agree? Now, I want your program to do the following. Given Java file like that, and given the variable name, tell me what the last dynamic type is for that particular variable, the last one. And the input here can be arbitrary. Again, if any one of you can implement a solution for this, you got A+. Okay, I'll get to that. Okay, are you thinking about you might do this? Okay, guys, don't waste your time. It's not possible. Let me be more precise. If you can give me a solution like that that really works, what you deserve is not an A+ in my course. What you deserve is a Nobel Prize. I'm not kidding. Okay? What I just described is a problem that's well known to be unsolvable by computer. That's why Eclipse does not implement it itself. All right? Because most of you are engineers, so maybe you wouldn't get a chance to take a course for theory of computation. I just want to mention some keyword to you, just for your knowledge. Okay? What I just described about keeping track of the dynamic type of some variable in a program that's arbitrary, it is so-called undecidable, which means a computer just cannot solve it. For proving it, let's not bother. Okay, just for your knowledge. Okay, you might be thinking that computer in general can do many things. That's true, but there are even more many things that computers cannot do, and keeping track of dynamic type is just one of them. Okay, so this one here is known to be undecidable. Okay, just cannot be solved. So that's why there's no other language like a Visual Studio, Eclipse, IntelliJ. Any compiler does not really allow the cast situation that I just mentioned. All right, just not possible. Okay, so why am I talking about this? I just want to tell you that keeping track of dynamic type is actually way harder problem than you might think. So for simple scenario like this, you might be thinking maybe compiler should do that. Yes, but not in general. So that's why it wouldn't do it. Okay. Now, why do we need typecasting? Because compiler cannot solve it, why don't we solve it as a programmer? If I know very well that for my program, at this point here, if I know Jim is indeed pointing to dynamically some resident students, I can let the compiler know, just trust me, just do it. Seriously, that's what it really means. For typecasting here, we are going to show to you, whenever you put a cast over here, you basically tell the compiler, do it, and then I'll take the responsibility. All right, that's typecasting. Okay, let's now learn about the syntax, and then I got to talk about different scenarios you might run into for typecasting. All right, so this one's done here. Okay, this is something we actually spoke about, when we talk about the equals method. But let's now repeat a little bit. So the syntax will be, you got some reference variable, and then you got parentheses over here, have some class name. And for now, let's keep it simple, just for one moment. Let's say whenever you want to do typecasting, you simply cast that into the same dynamic type, just the same. Okay, just for now. What's going to happen? Okay. To start with, we got Jim pointing to dynamically resident student objects, and the static type of Jim is students. All right, that's how we start with. The right-hand side over here for the cast is going to create an alias. And notice that we never ever modify the static type of Jim. It remains to be student. We never modify that. We basically create just an alias pointing to the same object here without any name. But that alias has the static type corresponding to the cast type. So I'm going to put resident student here. So now this resident students can fulfill the substitution rule that we spoke about earlier today. So if you try to say RS over here, can RS point to wherever this alias is pointing to? Yes, now we can do it. Because this alias here has the static type RS. Can RS fulfill resident students? Yes, it can. That's the trick. If you only try to say RS is assigned to Jim, you cannot do it, because students cannot fulfill resident students. On the other hand, if you say RS is assigned to this alias here, which has the static type RS, can RS satisfy RS? Yes. All right, so that's the logic you want to go through. All right, so after this reassignment over here, RS over here is going to point to wherever this alias is pointing to. RS. And it has the static type resident students. That's what's happening in the typecasting. And the very reason that we have to do typecasting ourselves is because compiler is simply cannot keep track of that dynamic type, as I explained to you. All right, any question about typecasting here? Syntax, we have seen that before, so I don't need to repeat too much. But just like a recall of the detail. All right, let me show you a little bit of syntax, and then we're going to talk something that's slightly more complicated. Okay, syntax quickly, and then we'll take a short break. All right, so for the syntax here, so this is the name. So you can see here, you can also look at this particular example here, right? So we know that a phone dynamically is iPhone 13 Pro. We're casting that to exactly the same dynamic type, so that's going to work. And then we can, once we cast that already, so you can see iPhone 13 Pro is the static type for the alias. Can iPhone 13 Pro fulfill iOS? Yes, it can, because iPhone 13 Pro can fulfill iOS. So this reassignment is fine. Okay, that's the only detail I want to watch out for. Now I want to show you some syntax which you may be interested in writing in your lab or maybe in the programming test. Let's say we have a phone over here, dynamically iPhone 13 Pro. Let's say you don't really want to bother with some intermediate variable. Let's say you can do that. The way to deal with it would be, I try to do the cast over here, surrounded by some parentheses. That one there is going to give you the alias of static type iPhone 13 Pro. After that, you can say dot, some method name. All right. So this will be the syntax you can learn. You can think about this one here. just this part here, the cast. So this is an alias of static type corresponding to the cast type. iPhone 13 Pro. And the reason that this will work is because iPhone 13 Pro does have the FaceTime as the expectation. All right. All right, that's an anonymous cast. And common error you want to watch out for. Take a look at this one here. All right. You might be wondering, isn't this the same? Not really. All right. This one here, basically, I took out the parenthesis over here. Is it still going to work? Not quite. Because you can see here, maybe the intention was you want to somehow do this, excuse me. The intention was you want to do the cast, and then you call FaceTime. But without the parenthesis, it's not the case. You can think about the dot notation here is so-called bind tighter than the cast operation. Think about this is more like a multiplication, this is more like an addition. All right, so if you don't have the parenthesis over here, this is what's going to happen. The compiler is going to understand this as follows. That means you want to call this method first, and then whatever that's returned from this method call, you want to cast that into iPhone 13 Pro. That's definitely not what we meant to do. But that's how the compiler is going to understand it. So this one here alone is not going to compile. Not compilable. Because the FaceTime is not part of the expectation of a phone's static type, which is smartphone. All right. A phone's static type, which is smartphone. All right, so that's the reason. Just remember, if you really want to use anonymous cast, you want to make sure you always surround the cast by parentheses so that it will be done first before the method call. All right, so that's the lesson. All right, any questions so far? All right, so I would suggest before I move on to the next two topics, the next two topics will be, we want to see when you do a typecasting, what will be the circumstances where the typecast will compile, number one. Number two, when the typecast compiles, under what circumstances is it going to be exception-free? Two things I want to talk about. Before that, let's take a short break and take attendance. Okay. So, before the break, we revisited the syntax for typecasting and also why do we do it, and also the consequence of doing it, right? Just don't forget an alias. And I'm going to talk about two important things. Number one, what kind of cast can you do to make your program still compilable? Number two, given that your cast is compilable, will there be any circumstances where the compilable cast might run into some exception, so-called class cast exception? I'm going to talk about these two together. And guess what? To understand these two ideas, we still got to talk about expectation. No way around. Okay, expectation. One at a time. The easiest way is to use an example. So let's now talk about compilation only. When we talk about compilation, you don't care about dynamic type, just static type. Let's say we have my phone. Yep. Declare to have static type Android. And I'm going to mark it on the hierarchy. This is my static type. All right. Now, what kind of cast can I do? Before, we can assume every time you try to do typecasting, given that, for example, let's say we know pretty well, the Galaxy S21 Plus is dynamic type. We'll just cast to that. It usually just work. But we want to make it more flexible, more general. Here is a rule. When you want to do typecasting, you basically can cast the variable to either its static type's ancestor or cast to its static type's descendants. Either way. All right? So in this particular example, right, I'm going to show you the table in a moment, but this is what you can do. Given that my phone is Android, you can either try to cast upwards to any of its ancestor. That's so-called upward casting. The other direction, you can also cast that to any of its descendants, of course, including itself. And if you do the casting there, it will also compile. So you can follow the link, just cast to any of the descendants. That's called downward casting. So this implies, what does it really mean when the cast does not compile? If you try to cast Android into a class that's neither ancestor nor descendants, it will not compile. As simple as that. All right. Now, let's now think about this table here. So what do I mean? All right. So let's say, talk about my phone first. Static type is simply Android. What will be the expectation? Expectation will be surf web, Skype, and dial. So let me fill it out. So for my phone here, it's going to be dial, surf web, and also Skype, right? So these are the three expectations for my phone. And the rest will be not applicable. They are not part of the expectation. Question for you, intuitively. If I do upward casting, am I effectively reducing the expectation or increasing the expectation? Reducing? Yeah. What about downwards? Increasing, right? Why? It goes back to our discussion. If I say I now want to upcast Android into smartphone, now I'm reducing my expectation to only these two. Without Skype, I'm throwing that away. On the other hand, if I do downward casting over here, for example, if I downward cast Android into Samsung, I'm basically saying now I want to have side sync available for me to call as part of the expectation. All right, so downward casting increases the expectation. Upward casting reduces the expectation. All right, let's verify that. So smartphone over here, SP is smartphone, right? That's after the upward casting, right? By the way, so I can say this is upward casting. And Galaxy, this one here is downward casting, right? After doing this upward casting SP, we have reduced the expectation. So the one we have gotten rid of is a Skype, right? So that means I only got 1 and 2. And this one is gone, and these are also gone. Okay, reducing the expectation. On the other hand, if I try downward casting here, I'm basically adding more expectation. So this is now will be Galaxy S21 Plus, which is over here. That should have, for example, side sync, right? So that's really in addition. So we got these for sure, and also we got side sync. That's the additional one. Okay, so this page tells you, as far as compilation is concerned, you can cast a reference variable to any of its static types, ancestor or descendants. You gotta be aware of, if you upcast, reduce the expectation. If you downcast, you increase the expectation. Just before your question here, just give me one moment. Let me say one more thing. When you do upward casting, you're basically reducing the expectation. Reducing expectation is not that dangerous. However, if you try to downcast, there is a potential danger. For example, let's say if the dynamic type is currently Galaxy S21 here, plus. Let's say this is a currently dynamic type. If you happen to downcast to this class here, you're safe. However, what if I downcast to Huawei? Can this actual dynamic type fulfill this cast type? Not really. So this is a danger, meaning that you have some downward casting that compiles, but it cannot be fulfilled at the runtime. So this is where the class cast exception occur. That's something I'm going to talk about next. Before that, question. Yeah. Mm-hmm. Exactly. Yeah, that's what I wanted to say. Yeah. So I'm gonna summarize that in a moment. That's exactly what you wanted to ask. Yeah. Bear with me. Okay. So this page here, compilation. All right. Let's now go over this example here using student class, and then I'm gonna write down the detailed reasoning. We'll see how much time we got left, but we're pretty much we'll cover many things today, which is good. All right. Let's now take a look at these three lines. So here we got Jin declared to have students static type here. Dynamic type is non-resident students, which is over here. All right, number one, compilation. Does this class cast compile? Does it compile? Remember, the principle is if you either upward cast or downward cast, it will compile. Is this downward cast or upward cast? Downward. Good. Because it's downward cast because you're trying to cast that into resident students, which is over here, right? This is a cast type. You're basically casting from students into resident students. Nothing wrong, compilation-wise. Nothing wrong. Downward cast. Compiles. However, when we try to execute it, you're going to see the problem. But before that, I'll answer the question. Downward casting. Okay, downward cast relative to the static type. Okay, so because remember when we talk about upward downward, it's really about compilation. Okay, so this way we got Jin declared to be students, which is here, and now we want to cast that into resident students, so it's downward casting. Okay, now let's say it compiles, and now let's execute at the runtime. Okay, runtime. Runtime, what's going to happen is, number one, RS is expected to be used as, you can see the RS over here is declared to be resident students, right? Declared to be used as resident students. But what's happening here? Let's visualize that as well, right? Let's make sure we understand this one very, very well. After line number one, we got Jim dynamically pointing to some non-resident students objects. Okay, this is non-resident students objects, and with a static type students. And in order to do this cast over here, we created an alias over here that has the static type resident students. And then we try to do this reassignment over here, and we reassign that to RS, declared to be of static type resident students. Right? That's a typecast. Now, what's the issue here? RS declared as resident students is expected to be used as a resident student. For example, premium rates. Can non-resident student here fulfill premium rates? Not really. It doesn't have premium rates. You only got discount rate. So there's some inconsistency here. So the issue is dynamic type cannot fulfill the expectation for the class cast type. So that's how we got class cast exception. Okay, let's now complete this reasoning here. So this is number one. I'll put number two here. Number one, the dynamic type NRS cannot fulfill the expectation of RS, which is resident students. And this is going to give you the so-called class cast exception. And you can also look at the slide, which also try to show you the reasoning bullet points. You can also take a look. Okay, I'll take question first. If we got enough time, we can do one more. Otherwise, we can continue. I'll go with you first. Yeah.
So just make sure downcast descendant and upward descendant with the ancestor. So if it's in that weird situation where it's a sibling or that kind of situation.
If you try to cast, for example, if you try to cast to the static type sibling, it's not even going to compile.
So this case, like, it has to first do downward or upward, and that compile.
Okay, how about this? So class cast exception can only occur when you try to do some kind of downward casting, because downward casting is going to somehow increase the expectation. But the problem is the expectation that's increased may or may not be actually fulfilled by the actual dynamic type. It may or may not be. That's the issue. Okay? If it doesn't compile, for example, yeah. So let's say, let me talk about doesn't compile case maybe on Tuesday. Okay? But for now, just remember, when I got students and with the dynamic type non-resident students, but if I try to do downward casting into this, compilation is okay. But at the runtime, can the resident student's expectation be fulfilled by non-resident student? No. Class cast exception. Okay, yeah. At the runtime, as soon as you hit this class cast over here, you're gonna have the exception. Think about this one here. So this is where the exception is gonna occur. And think about at the runtime, class cast exception. Sorry, you got a question? Go ahead. Okay, I like that question here. Okay, guys, final one. Let me make a remark and then we're done. Okay, please. So let's say this. Let's say at the moment we don't have any premium rates, we don't have any discount rate. Effectively, these two classes are identical, let's say. Now, if I still got the same setup over here, students with dynamic type non-resident student, I try to cast that into resident students, I will still get into class cast exception. Similar reasoning, because resident students in general, in the long term, may have some added attributes and methods that will make it incompatible with the dynamic type over here. So we'll still run into class cast exception. All right, thank you so much. Review this, and then we'll continue from here to conclude next time.